Okay, so last time we started on section 3.4 on sequence spaces. So first of all, we were looking at the sequence of all, well, the set of all sequences of elements of our scalar field f, which was f to the power of the natural numbers, which you could also regard as the product of over all natural numbers n in the natural numbers n of a copy of the scalars.
A short question, by the way.
Yes?
Does that n belongs to natural numbers? Does it mean that it goes from n to infinity?
So the n in the natural numbers for us starts from 1. So the product, can you ask me your question again? I think you said, does it go from n to infinity, did you say?
Yeah, from n, I mean 1 to infinity.
Yes, from 1 to infinity, yes.
Okay.
That's right. So you could regard each of these as a separate space, but they all happen to be the same. So you could say that this is xn, but where every xn is f. Okay, and that's absolutely allowed. Sorry, wrong f. Xn is your scalar field for all n. So it's a product of infinite many copies of the same thing, and as you say, that means you run from n equals 1 up to infinity. But not including infinity. The termwise operations, as I mentioned before, if you add two sequences, it means you add the first components to get your new first component, add the second components to get your new second component, and so on. Or terms, whatever you want to call them. Component-wise operations is another way. So again, I'm always running from 1 to infinity in this setting, unless otherwise stated. We had C00 as the so-called finite sequences, the sequences which had at most finitely many non-zero terms, and then the rest was 0. And that, as I mentioned, was the same as a vector space of polynomials with coefficients in your scalar field. And it's got countably infinite dimension because you can just write down a countable sequence which is a Hamel basis for it. Every element of every finite sequence is a finite linear combination of these sort of standard sequences which are 1 in a particular component but 0 everywhere else. And then we introduced the little LP spaces, which were those where the sum of the p powers of the modulus of the terms was finite. And then to get a norm on that, you took the p root. Here we're assuming p is greater or equal to 1 and strictly less than infinity for the moment. And then you get a norm. If you let p get less than 1, you don't get a norm from this expression. So there are things you can do with those spaces, but we won't deal with them in this module.
Wait a minute, is that LP, little LP, just discrete version of capital P?
Capital LP?
Yeah.
If you've done measured integration, which we haven't yet, then it is big LP with respect to a particular measure, and the measure is counting measure.
Okay.
So it's exactly the same as taking counting measure on the natural numbers, and then you can take big LP, and then what you get is exactly these little LPs. So these are a special case of something you can do in more generality with the measure theory. But we haven't done the measure theory, and we won't do enough measure theory to really get into that in this module, though there will be a bit of measure theory later. But certainly, if you do look in Rudin, real and complex analysis, you'll find that's the level of generality it's mostly dealt in. So you'll find a complete study of these LP spaces as big LPs, and with these little LPs as special cases, if you look in Rudin, real and complex analysis. And the theory is looked at from the measure theory and functional analysis point of view. So it's a good book to look at, Rudin's book on real and complex analysis. A bit concise, but very trustworthy. So little L1, sum of the moduli was finite, and that's your norm. L2, your norm, you have to take the square root of the sum of the squares, and that's a Hilbert space norm. Then we moved on to little L infinity, which is the bounded sequences. And C0, which is, as it turns out, it's going to turn out it's a closed subspace of L infinity consisting of the null sequences, those sequences in your scalar field which tend to 0. Convergent sequences are bounded, so that definitely is a subset of L infinity. I have some comments on the relative easiness of dealing with L1, L2, L infinity, and C0, and the fact that the little LPs needed Hulda and Minkowski if you want to check all the details. But you're allowed to quote, unless asked specifically to prove things of this nature, you're allowed to quote that these little LPs are vector spaces and that the norm P I defined is a norm on them. And I invite you to look in the books for the details in order to fill in the details if you want to find out about Hulda and Minkowski. It's an optional and interesting reading exercise. Which brings us on to this theorem that summarizes lots of stuff about these spaces. So we've got the sup norm on C0, and we've got little LP for 1 less than equal to P less than or equal to infinity now, because we've defined little L infinity as a special case, which again gets a sup norm with the bounded sequences. I claim that C0 is a closed subspace of L infinity, and we'll prove that in a bit. I claim that C00 is dense in almost all of these, with the exception of little L infinity, that's the only one of the ones I mentioned where C00 isn't dense. And we'll see various reasons why it's not dense in a bit. And there's loads of other sequence spaces. I use sequence spaces quite a lot to give examples of Banach algebras, in fact. So if you look in some of my papers or in Garthdale's book on Banach algebras, you'll find there are loads of examples around. They're a bit more interesting than these. These are interesting enough, but it doesn't tell the full story. There's a huge variety of sequence spaces with an amazing number of different properties. But this is enough to get us started. And it's more than enough to keep us busy for a while. And the completeness, of course, we've got to prove. Perhaps not for everything, but I will give you a few completeness proofs. And they follow a similar structure, though maybe slightly easier than the completeness of the continuous functions on closed interval that we did earlier. We will, however, have to have some notation for sequences of sequences, which actually there's lots of different choices for notation to use, so I'll just give you one that you can work with. Right, so where shall we start? Let me start by saying we already know that C0 is a subset of L infinity, and we've already seen an example of a sequence that's in little L infinity and not in C0. This is not surprising. There are rather a lot of them. Indeed, the sequence 1, 1, 1, 1 is another sequence in L infinity that's not in C0, because anything that's bounded but doesn't converge to 0 will do. So it's clearly we have C00 is a subset of C0 is a subset of little L infinity. Well, I mentioned why C0 was a subset of L infinity earlier. C0 is not equal to little L infinity. For example, the sequence 1, 1, 1, 1, and so on is in L infinity and not in C0. So once we show that C0 is closed in L infinity, it'll follow that C00 is definitely not dense in L infinity, because the closure of C00 is going to be a subset of C0. Now, where is my add more space tool gone? There it is. There you go. It'll then follow that C00 is not dense in L infinity, because the closure of C00 will actually likely be C0, which will be closed in L infinity. But no subset of a proper closed subspace can be dense. Okay, so that will do that. So also, once we've shown that L infinity is a Banach space and C0 is a closed subspace of it, that will make that C0 is complete as well. So the completeness of C0 also follows once we have shown the completeness of L infinity. And then C0 is a closed subspace of L infinity, so it'll be closed when you restrict the norm, but the norm on C0 is the restriction of the norm from L infinity. It's just a suit norm again, norm infinity. So that will do some of it. So let me prove for you that little L infinity is complete. We need some notation for sequences of sequences. So we have the problem that we're going to be writing x equals xn, n equals 1 to infinity, which equals xn, will be just one sequence in f to the n, typically for us. So if we want to have lots of them, we'd like to say xn, except that xn is already a term of xn. So you can either go for double sequences, or I'll use a notation that I saw in Cambridge when I was first taught this stuff. I'll put a k in brackets at the top to mean each of these is a different sequence. For a sequence of sequences where we will say that xk is the sequence xk1, xk2, xk3. So in other words, so we'll have xkn's in F. And xk will be the sequence xkn, n goes from 1 to infinity, in f to the n. And then our sequence of sequences will be xk going from 1 to infinity. So that's the notation we're going to use. Are people happy with what I'm doing here? What lies where? So if I write xk, I'm probably going to mean that is the xk itself is a sequence with terms xkn, n runs from 1 to infinity. And then, of course, I'm going to have a sequence of sequences because maybe xk is a Cauchy sequence in little l infinity. And so let's see this. Just again, I'll ask any questions about that before we see it in action. Okay. So now, let's suppose you've got a Cauchy sequence in little l infinity. So k will run from 1 to infinity. Of course, using the suit norm. And we have to prove that this sequence converges in L infinity. And as usual, we split it up into two stages. It's a two-stage proof, where the second stage is really, I think of it as two stages combined. So stage one is to show that the xk converge term-wise to something. I'll explain what I mean by that in a minute. So they could converge term by term or component by component to something, to some x in f to the n. But by this we mean xkn will tend to xn as k tends to infinity for each n in the natural numbers. So you get one sequence for every term. And here, as usual, we're using the usual notation as above.
So shouldn't that let just plain x be sequence?
X is an element of the sequence space. So x is equal to xn. And this is the typical notation we're going to be using. But it's a good question. Okay? So notation is as above, which means that if I say that x is in the sequence space, I'm going to mean that x is a sequence with terms xn. And these xnk's, so the xk, remember, each xk is a sequence, so xk is equal to xkn, where n runs from 1 to infinity, So this is the notation I'm using here. If x is a sequence, it will have terms xn. Each xk is a sequence, so each xk has got terms xkn. And now if you take any particular natural number n and let k vary, I'm going to claim that xkn is a convergent sequence and it converges to something which we call xn, and then you put those xn's together to make a sequence x. Does that make sense? Okay? So that's our notation for this stage. Now to prove this, that's going to be stage 1. Stage 2 is the usual bit. We have to show that x is actually in L infinity and that the xk's converge to x. So that the uniform norm of the difference has to tend to 0 as n tends to infinity. As k tends to infinity. I'm bound to get into trouble with my k's and n's. If you spot that my k's and n's have got swapped, do let me know. So, are people clear on our strategy? We're going to check each component. This is the easy bit. Stage 1 is always the easy bit, and stage 2 is the bit where you have to work a bit harder. So, okay. Here we go, for stage 1. Let's let n be a natural number. Then for all k and m in the natural numbers, we have an estimate on how far apart the nth terms are, modulus of xk n minus xm n. That's at most equal to the uniform norm of the difference in the sequences xk and xm. Just rewrite that. Soup norm. Okay, remember the soup norm, this uniform norm, this infinity norm is you take the supremum of these things. It may not be a maximum, but it is the supremum of them. So it will be greater or equal to any one of them. So when you take the difference of the sequences, of course, you take the difference term by term. So it's going to be greater or equal to any single difference in terms. So n is temporarily fixed at the moment, and we have this inequality. But we know that the xk are a Cauchy sequence, which means that when k and m are big, this is going to be less than epsilon. It follows immediately, especially if you write a few extra lines, but which we won't bother. We now say it's now clear that this sequence here, xkn, of scalars, is a Cauchy sequence in F. So since xk is Cauchy in L infinity, it follows that that's when k equals 1 to infinity. And again, when you look at any particular term, you still let k go from 1 to infinity. And that's now a sequence of scalars, and that's now a Cauchy sequence in F. And so it converges. Then, of course, you set xn to be the limit. as k tends to infinity of xkn, which is of course in F, and you set x to be xn, n equals 1 to infinity in f to the n. And we've finished stage 1. We've shown that they converge term-wise to something. So, remind me what we have to do next. What was stage 2?
Allegedly, we have to show that this x is in L infinity and that the are sequences of the xk.
Okay. So that's right. We've got to show that this is in little n infinity and that the xk, the sequences xk, do converge to this sequence x in the uniform norm. So stage 2. And we'll do this in one go. We'll let epsilon greater than naught, and we'll show that from some term onwards, the uniform norm of the difference is less than epsilon, which will automatically show that the x has to be in L infinity at the same time. It's a little subtlety, that, though. So let epsilon greater than naught. We show that there exists a capital number n such that for all n greater or equal to capital N, we have, I'll use less than or equal to just to save myself some trouble. We have that xn minus x is in L infinity and norm xn minus x infinity is smaller or equal to epsilon. I'm being very careful there. You aren't even allowed to take the sup norm until you know it's in there, unless you want to allow the possibility of infinity. You can rewrite this. If you do want to allow the possibility of infinity, you can just say so that this is less than or equal to epsilon, in which case this bit about being in L infinity also follows. And once that's in L infinity, the result will follow because x will be the sum of xn minus x, let's get this right, it'll be the difference of xn and xn minus x, which will therefore be in L infinity as well. The result follows from this since x is equal to x minus, is equal to xn minus this thing, will then be in L infinity as well. Well, we're just going to use the cosinus. So since xk is Cauchy, choose n in the natural numbers so that, what have we got here? Tell me what I've done wrong. And anything else? What is it? What is xn and what is x? Xn is a scalar. I've got completely wrong notation here. So it doesn't really matter whether I use n's or k's, but I think while I'm fixing it, I'll fix it thoroughly and get all the notation right. We have the sequence xk minus x should be at L infinity. The sequence xk minus x should have norm less than equal to epsilon. And x is equal to xk minus x And now I'm not trying to subtract a scalar from a sequence, which I suppose one could do, but it surely wouldn't be right. So I'll choose an n in the natural numbers so that for all k and m greater or equal to capital N, we have the norm, the sup norm of xk minus xm will be less than epsilon. I can get away with less than or equal epsilon here because I'm using less than or equal epsilon further up. But this is going to be more standard if we're doing Cauchy. By the time I take limits, it'll become less than or equal anyway. Let's let, I claim this capital M will do. To satisfy the above facts, perhaps I should give that a name. Let's call that star. This is what I'm going to try to achieve, and I claim that this M will do to satisfy star. That from that point onwards, you're within epsilon of x. And once we've done that, we've finished. Well, it's the usual trick. We let n be a natural number. Then, and n is now fixed for a while. For all k and m greater or equal to capital M, we have similar inequality to before. If we just look at the nth term, this is one of the terms of the difference of the sequences. So that's going to be less than epsilon as well. So fixing a natural number n and some k greater or equal to capital N for the moment, you can let m tend to infinity so that after a while it's bigger than capital N to obtain modulus xnk minus, well, as m tends to infinity, this xmn tends to just xn. But it becomes less than or equal to epsilon. So what did I use there? What did I do when I let m tend to infinity? Obviously, after a while, m is at least capital N. So that's why I was taking a limit of things less than epsilon. What else did I use? I mean, I'm not asking for anything deep here. How did I get an xn in there? That's right, we had termwise convergence, and this is one of the terms. This is the nth term, which is fixed at the moment. If you fix n and let m vary, as m tends to infinity, the nth terms will converge to the nth term xn. That's all we're using. We're using our very weak fact to prove a strong fact here. As usual, it's a combination of a really weak kind of convergence along with this really powerful Cauchy condition that just tips the balance to make things work. But you do have to do everything in the right order. Now I fix k greater or equal to n and take the supremum greater or equal to capital N, and now I take the supremum over n. So with the same k, for this same k, take the supremum over n, to see that xk minus x really is in L infinity, and that the suit norm of xk minus x infinity is less equal to epsilon, as claimed, because this worked for every n and every k greater than n, and so you're allowed to take one of those and let the other one vary, and that's what we did here. And finally, this is true for all k greater than capital N, so the result follows. So that proves star. This shows n works for star. And the result follows. So these proofs are a little subtle. If you do things in the wrong order, things go horribly wrong. If you do things in the right order, they just work. And as I say, it's quite close. Cauchy condition is very strong. Cauchy condition is never very far removed from converging. If you could just get a little bit of extra machinery in to help, Cauchy you can normally get from Cauchy to convergent. Of course, we bootstrapped. We started by using Cauchy to show that the sequence is converged term-wise to something to get us started. Then once you've got a likely limit, you come back and use the full force of Cauchy to show that it really is a limit in the norm you're dealing with, in the middle of which you use the term-wise limit to help you. Just fix one of the estimates. Are there any questions about that proof? Now that we've fixed all the notation. Okay, so there's one of our more interesting Banach spaces so far, a nice infinite dimensional space. It's actually not a very nice space, little n infinity. It doesn't have a countable dense subspace. One can prove. That's going to be on one of the question sheets. So this is not a separable Banach space. And once Banach spaces are not separable, they are actually quite unfriendly. And a lot of the machinery, a lot of the machinery that we use, again, the stuff you can do for separable spaces that doesn't need the axiom of choice. But as soon as you start trying to prove things for little n infinity, it being not a separable space, you're going to have to, really will have to start using the power of the axiom of choice for that, implicitly or otherwise. Okay, what about C0 being a closed subspace of L infinity? Because that will handle two of the other statements at the same time. I wonder, usually I do this using sequences, but I wonder whether I should try and do it by showing the complement is open for a change. It's an option. But I think I better stick to sequences again. So we'll do sequential closedness. Okay, this is the sequence criterion for closedness. What is the sequence criterion for closedness? We've had this in one of the earlier lectures.
That all convergent sequences in that field converge in some.
Okay. That is, perhaps rephrase that slightly, but that's the idea. You look at any sequence in C0 that converges in L infinity to something, and then you have to prove that the limit is still in C0, which is basically what you said, but just removing any ambiguity from it. Okay, so So let xk be a sequence in C0, and suppose that this sequence of sequences tends to x for some x in L infinity, and this is with the notation as above. So we know what all the terms of these sequences are. I'm not going to have to keep telling you that all the time. And of course, with respect to norm infinity. We have to prove that x is also in little c0. Okay, well, I'll do it all with epsilons again. I've got to prove that from some term onwards, perhaps I'd better remind you this notation. We have xk is equal to the xk n runs from 1 to infinity, and x is equal to xn, n runs from 1 to infinity. So let epsilon greater than naught, we have to show that there exists an n in the natural numbers, so that for all n greater or equal to n, we have modulus of xn is smaller than epsilon. That's what it means to check that a sequence tends to 0. And we know that's true for all the approaching sequences. I think I'll do an epsilon over free proof for this one. I could have done a free epsilon proof. So start by choosing n1. Actually, no, let's just choose any old k such that the uniform norm of xk minus x is more than epsilon over 3. We know there are some because they're converging to it. This k is going to be fixed now for the rest of the proof. And you choose capital N so that for all n greater or equal to n, we have modulus of xkn, this particular fixed k, is less than epsilon over 3. And this capital N we claim is good enough. So again, we'll claim that n satisfies star. Well, I better tell you what star is. Star is always the nearest star. Well, we have for n greater than capital N that mod x, I bet I've overdone this, let's have a look. Mod xn is smaller or equal to mod xn minus xkn plus mod xkn. And it looks like I've really overdone it. I could have done epsilon number 2. Who cares? I'm going to have room to spare. That's less than epsilon over 2, because the uniform norm is less than epsilon over 3, in fact. So I can have epsilon over 3 there, plus epsilon over 3 there. And I could have used epsilon over 2, but it's definitely less than epsilon. What did I use? That's because that's one of the terms of the differences in sequences, and the sequence, the difference in the sequences we said was less than epsilon over 3. And this one was just for n greater than n, we had that we knew that this was less than epsilon over 3 as well. So sum of two small numbers is very small, and we finished. Any quick questions on that proof? I must remember to use epsilon over 2 next time. Okay, we'll stop there.